So welcome to this new topic. It is called deformation, or in bracket the stretching of materials or stretching materials. Okay, so we are going to be looking on this topic on how we're still in the area of mechanics in the syllabus, right? We're still studying how forces affect the function of how forces affect bodies or objects within the environment. In this topic, you'll be learning how forces cause deformation, or the stretching of materials, or the changing of the shape of materials. Because as you know, when you stretch something, its shape changes, right? So the subtopic of that will be Hooke's law. Will be what? Hooke's law. Now, Robert Hooke was a English scientist, right? And he was born in 1660. And he basically was responsible for formulating what is called Hooke's law, which you'll be learning of. Okay, so enjoy. So this is the setup for the Hooke's law experiment to prove Hooke's law. So we have a retard stand, we have a ruler that is held in place, right? Has to be held in place. We have another clamp here, and we have a spring attached to the clamp, and we have a pointer attached to the spring. Each time that we're going to test how far the string will stretch under a given force, we attach slotted weights. So we have a 20 Newton weight here, for example, and we basically attach it to the spring and see how far the string stretches, and measures that. We measured it, right? And the ruler. So this pointer right here, when the string stretches downward according to the pull of gravity and the weights attached to it, then the pointer would obviously give point some part to the ruler where we can get an accurate measurement, right? We add an next weight to it, and then we measure to see how far it stretches again. And we continue doing that process for about 5 or 6 trials, right? And then now we would have our results of extension, right, which is the measured distance in centimeters or millimeters of where or how far the string stretches to, and we will have the force. We will know the force that we attach each time. So the 20 Newton force, how far did it make the string stretch? The 40 Newton force, how far it make the string stretch, the spring stretch, and we continue that on, right? So we have those extension values, which is the distance the spring has stretched, and we have the force that we use each time. We can populate a graph. And this is the Hooke's law graph. It is a graph of, and you must understand this, extension versus force. Okay, so that is the Hooke's law graph. And the Hooke's law graph is a straight line graph. It is a straight line graph. You would have your extension force here in newtons, right, on the x-axis, and on the y-axis you would have your force here, rather, your extension force, the force that causes the extension, and the x-axis. And you would have the distance it extends to in millimeters or centimeters on the y-axis. Okay, so when you plot those graphs, if you should do the experiment and you plot those graphs, you should get a straight line graph if you never stretch the spring beyond its limit. Okay, so that is a setup right there, and this you will be doing for a lab. So get well acquainted with it. So that is how you test for Hooke's law, that setup. Appreciate that for CXC. Alright guys, so welcome to the new topic, and the new topic is Hooke's law. The new topic is Hooke's law. Now, Hooke's law states that the extension of a spring, right, and we're still in the area of mechanics in physics. We have not come out of mechanics as yet. We have some going to go before we actually get out of it, go into thermodynamics. So we're still in mechanics. We're still studying how forces affect bodies, right? How forces affect objects in our environment. So Hooke's law is a good way of appreciating how force causes stretching, how force causes the changing even of shape of objects, whether you're compressing something or whether you're stretching something. So Hooke's law enables us to get a good understanding of that. So Hooke's law states, and you have to memorize Hooke's law. Hooke's law states that the extension of a spring is directly proportional to the load or applied force, which can be considered as a stress, right? Provided the elastic limit is not exceeded. So what does Hooke's law state? Hooke's law states that the extension of a spring is directly proportional to the load or applied force, right? Because you know, say by now you know that a load is a type of force, right? And it actually causes stressing on the material it is placed on, provided the elastic limit is not exceeded. So there is many things to define. Elastic limit, right? This might sound big to you right here, directly proportional and everything like that. Well, it's not that hard to get to the bottom of. You see the Hooke's law graph? The Hooke's law graph actually allows us to see Hooke's law come into being. On the x-axis, you would have your stress force. The Hooke's law graph, a graph of extension versus force. Extension distance in centimeter or millimeter, right? Versus the force that is placed on it in Newton, right? So you would have definitely have appreciated thus far from observing the diagram that we saw on the chart, right? In how to really and truly carry out the experiment. You would have seen the experiment and you would have appreciated how it is done before we can even define what Hooke's law said, right? So if you have extension and you have force, right, this is how the graph would look. The force would go on the x-axis, the extension distance would go on the y-axis. They say it is directly proportional. You see this straight line graph is telling you that it is indeed directly proportional. Directly proportional means that when the load that was added to the spring goes up, then the extension of the spring increases as well. The more force you add on the string, the greater the string's extension, or the farther distance the string will stretch. That makes common sense. That makes a lot of sense. All of you guys have actually stretched springs already, and you have seen that the greater amount of force you put on the string if you pull it with your two hands, this farther the string stretch. So watch this. On a graph like this, say for instance, I put a 5 Newton force, and this is in Newton. These are the forces that were applied, say for instance from the slatted weights, and this is the distances that we were measured. So say for instance, I come here, and I put a 5 Newton force on it. I get a 9 centimeter extension, or 9 millimeter extension, right? I come here, and I put a 10 Newton force on it. I get a 20 millimeter or 20 centimeter, depends on what unit we use, extension. And you see the same thing for 50 Newton. It continues to go up and up and up. The farther the more force I put on this spring, the farther the spring will stretch. And if you were stretching a metal wire, even though the wire not curly, if I want wire you use stretch it same way, it would behave similarly. Okay? So there is something that is coming out to us called the elastic limit. The elastic limit. It must be something that you can identify from a graph, from a Hooke's law graph, if it is given to you, and it must be something that you must also memorize and appreciate it. Okay? But before we go there, let me give you a little summary of what this Hooke's law is saying right here. So if you want to summarize everything what the Hooke's law said, we could have said this. Extension is directly proportional. So that symbol there means directly proportional. It looks like a wrong bang. Extension is directly proportional to, let me erase the graph now, to right, to stretching force. So that's a shorthand way of writing, of expressing what it is saying. But you must memorize this. CXC is going to want you to literally put that back on paper if they give you in a question. You must understand that Hooke's law states that the extension of a spring is directly proportional, meaning when force go up, extension increase, distance increase. If I take off some of the force off of it, then it will drop. Say for instance, I am at 30. Let's start at 30, right? So for instance, here would be 20 Newton. But suppose if me take off 10 Newton of force. You see, say 10 Newton, 10. Let's start here. Say here was 20. At 20, the extension is 30. But if I take off 5 newtons of force, I am coming down to 20 centimeter. I take off 10 more, right? And I'm coming to 17. I take off, I'm at 5 Newton now. I come here, I'm at 10 centimeter. So if I increase the force, the extension distance goes up. If I decrease the force, the extension distance goes down. And this is what directly proportional means. Directly proportional means if two things have a directly proportional relationship, when one of them go up, the other one has to go up too. And when one goes down, the other one has to go down as well. So I want you to appreciate that, right? So if the extension force right here goes up, the distance goes up. The extension distance goes up when the extension force is increased. And if the extension force is decreased, moving from 20 come down to 15, extension will go down. Extension is going down, right? That's how that graph is read. And Hooke's law is a straight line graph. Straight line graphs tell directly proportional relationships. Guys, so let's see, before we go and do the definition of elastic limit and how it really and truly is related to Hooke's law being conserved or being kept, let us lay some ground rules first. Let us make a statement first. We all know that springs and metal wires can be stretched. By now we know that, right? And we have mentioned the term elastic limit. Have you ever stretched a spring? Probably have taken a spring out of a toy or something and stretched the spring until this spring cannot come back to its normal shape. Have you ever done that? I'm sure most of you had. If you can get a little spring right now, you can play around with it and try to stretch it. Don't stretch it a lot, but when you stretch it, the spring comes back to its normal position, or its normal shape, right? But if you put a lot of force on it, that spring loses its shape and it becomes stretched out. All of you have done that, and if you have not, you could try. It would be a wonderful example of how elastic limit comes in. And elastic is not pertaining to elastic bands, okay? In this topic, elastic pertains to really and truly the deformation of or the stretching of materials, okay? So elasticity can be expressed in metal objects, not only rubber bands, okay? And even plastics can basically express elasticity and stretching as well. Obviously, every one of you guys have stretched a plastic bag. Alright, so just get that out of your head. Say the word elastic in physics is pertaining to an elastic rubber band. No, not in physics. It's more pertaining to the ability of materials to stretch. Okay? And they don't behave like elastic bands also, because I must state something, that elastic bands does not obey Hooke's law. They do not what? They do not obey Hooke's law. Okay, so I'm just putting that out there. Rubber bands do not obey Hooke's law. We're dealing with metal springs, you're dealing with metal wires. Okay? Now, if you continue to stretch a spring or wire further and further past its elastic limit, the stretching becomes permanent and the spring or wire will never go back to its original length. When this is done, you have passed its elastic limit. When you stretch the spring until the spring can't come back together, right? Until the spring just stretch out so, it cannot obey Hooke's law at that point in time again. Okay? And also, really and truly, you have passed its elastic limit. Okay, so when elastic limit is passed, the spring no longer obeys Hooke's law. Just putting that out. Or the metal wire does not obey Hooke's law when it stretches out to so far that it cannot come back again. Alright? right? So let's define elastic limit, right? So elastic limit can be defined as the maximum extent, and you must memorize this definition, the maximum extent to which a solid, example springs, and metal wires, right, may be stretched without permanent alteration of their size or shape. Okay, so that's elastic limit defined for you. Note also, Hooke's law is not obeyed or it does not apply past the elastic limit. If you make a spring past the elastic limit when you can't regain back in shape, right? When you get in shape get permanently altered, Hooke's law not apply to it again. Okay, you must appreciate that. Guys, so this graph is showing us as another Hooke's law graph, right? But in this graph it is actually showing you how the elastic limit can be expressed on a Hooke's law graph, right? We have points A, we have points P right here. I have not put numbers on the graph, but just appreciate in the back of your head, so the values that have been there. It was a graph that was populated with information, right? The force, as we always say, goes on the x-axis in a Hooke's law graph, right? And the force can also be the weight. Force in this case would be the weight at the slatted mass, also obviously, and the extension would go there, right? Extension distance in centimeters. That's extension, not written pretty, but it's extension. Okay, you see from points A to E, Hooke's law is obeyed. There's a straight line right here. So from this point A, right, from the origin all the way to E, Hooke's law is obeyed. Okay, definitely obeyed. And within this range, the weight placed on the spring is directly proportional to the extension that the spring will stretch to. All of that from A to E, that is the case. Okay, but you see, from E to B, right, if you continue stretching from E and reach B, everything along that line right there, that curvature, where the line starts to curve, that is where the elastic limit is surpassed. Right there, so right at E, the curvature upon the graph come. And when the Hooke's law graph start move from a straight line to a curve, anywhere that curve begins, that is where the elastic limit is, right there. So anywhere along this line, if the stretching is continued from E anywhere to B, a permanent stretching is the result. Permanent stretching is what? Anywhere along here, permanent stretching is the result. When the load is removed, the spring now, if you take off the load off it, you know what the spring I go do? The spring I go contract, or the way I go contract to point P, right? And the graph. That is what you would legit see if you had values. If you remove the weight, you would have contract and move to the point P and the graph. Right? So therefore, that would show you the permanent stretching of the spring, right? So if you stretch anywhere along if you stretch the spring anywhere past P elastic limit, which is between here and there, anywhere along there, you can't get him to come back, people. That's it for the spring. And Hooke's law is obeyed all the way here. From here, Hooke's law is obeyed. Everywhere along from A to E on the straight line, Hooke's law is obeyed. It's not obeyed from E to P. It's that's not the case, right? From A to E. Anywhere along here, Hooke's law is not obeyed. It's obeyed anywhere along the first straight line, not obeyed here. Okay, along the elastic, when the elastic limit is surpassed at E and the curvature start comes. Anywhere from E to B, it is not kept. Okay, it is not obeyed. And you must understand that a permanent extension will be the result. With more contract and come back up P, spring losing shape for good. Okay, but if you put it back in our machine, smelt it, melt it down and remake it. Okay. Alright, so on our next note, so you have learned the elastic limit on a graph, right, expressed on a graph, and how the Hooke's law is not obeyed along that distance, along the curvature. You have learned where to find the elastic limit on a Hooke's law graph as well, and where along a Hooke's law graph, even if elastic limit is there, where along that graph is Hooke's law obeyed. You have learned all of that. Now you must learn how to extrapolate information or take information from a Hooke's law graph. The method is similar for taking information from any other graph, right? With a curved line or straight line or whatever, right? So in a Hooke's law graph, you may be asked on CXC, find the weight of the mass, find the weight of the object from a Hooke's law graph, right? And you might not have been given the results, yet they might find the weight. Them just get this graph populated. They have values like 5, 10, 15, 20. You have like extension 1, 2, 3, 4 centimeter, right? You may be asked the question, how do I find the weight of the object? As I said, the force is going to be the weight of the object. All along this is the weight. But they might ask you to plot the points first and then give you the weight for something that you did not originally have. Or what weight would that be if the extension was such and such? So say for example, find the weight of an object in which the spring in which it causes spring to extend to 3 centimeter. Alright? All you would do, start at 3 centimeter, and some of you that have taught physics would have learned how to even do this from a previous graph, how to take information from a graph. Start at the 3 centimeter, take your ruler, straight line, have to be straight, can't do it freehand like me, right? And anywhere it touches the line, you bring it down, straight line again with the ruler, can't bend line to the curve. Right? Not to the curve, to the x-axis, right? So you start from where they say a force of an extension of a force applied to a spring cause an extension of 3 centimeter. Right? You can write that question down. You might see it again. Or questions like it. What weight would that force be? Alright? And you can use your graph. You can use your Hooke's law graph, and you can find out the weight of the thing. All you have to do, start at the distance of them give, the extension distance. Carry over the line and let it touch it. Have to fall right on the straight line. And then bring that down. The point where it touches the line, bring it down to the x-axis. So you move from y-axis, you touch the line and come to the x-axis. And that is telling us it would be, the weight of this would be approximately 15 newtons. So a 15 newton weight placed on this spring in which a graph like this would be generated would have to be a 15 newton weight for it to generate a distance of extension being 3 centimeter. Alright, so please be aware of that. That is how you pull information from a Hooke's law graph. You can tell even the extension. You don't have to only find out the weight or the force or the object we put on it. You can even find even the extension, the distances it would extend to. If you put such and such weights on it, you will probably never even have the weight them. You use 10 newton weight, 5 newton weight, 20 newton weight, and then now anywhere in between that you can literally tell, even if you don't have the weight on hand. Let's say for instance, the question is changed and they ask you, what is the extension distance that a force of 7.5 newton added to a spring, to the spring that was used to make this graph anyway. Can be any old spring. To make this graph, what extension would a 7.5 newton weight cause? All you do, since as the 7.5 newton, then you start with the 7.5 newton and you bring it up. Right? Same place, make it touch the line, have to touch the line, can't pass it, and you carry it over straight line. And according to this setup, it is saying that we would have an extension of about 1.7 centimeter. Right? 1.7 centimeter. If a weight of 7.5 newton was added to it, it would extend to 1.7 centimeter. That is the kind of information, that is how you pull information from graph. And not only Hooke's law, but many other graphs. But this is how you it's called extrapolation. Pulling information from a graph or from something. Okay? Guys, so we have made a statement a while back and we said that don't get the word elastic mixed up with just the word elastic band. right? Elastic in physics means the stretching ability of materials, right? That material can be a metal spring or a metal wire, okay? And other materials that also show forth the ability to be deformed or stretched or even compressed, right, is plastics. Obviously, you have stretched plastic bags and you have also folded them up in your hands, right? And elastic bands can be stretched, but they do not obey Hooke's law. All right, so we do not look a lot on elastic bands, but I would like you to understand why Hooke's law is not obeyed when rubber is stretched. All right, so this is an extension graph of rubber. Same force, same extension on it. Can someone tell me why this is so different from a Hooke's law graph? Where along this line do you see a straight line? There is nowhere. It's like an S. There is nowhere along it that Hooke's law could possibly be obeyed. Because Hooke's law say the extension force, right? Hooke's law say the extension force, so force is directly proportional to extension or vice versa. Extension is directly proportional to force, right? To the force applied. Means that when force go up, extension goes up. When force goes down, extension goes down, and vice versa, right? Nowhere along this line can that be said, because if we put extension there, right? If I put it there, for the force there, it goes there. You understand where I come from? But because it's so curved, it is not directly linear. Do you understand what I'm saying to you? There, if it is not directly linear, it does not go up piece by piece by piece by piece by piece. And if the curve continues, you understand where I come from? Look at it. It's gonna start really and truly adding back up. It start off, you might can say, well, it was obeying it about here. You understand where I come from? But the further you go up and the curve is shown, and this is in the loading stage. In the loading stage, when the weight is being added, you kind of want look like you want to obey it. But the more you go up and add the weight, continually adding the weight until it gets tough, it gets taxing on the rubber band, it starts to disobey Hooke's law, right? And even though you might remove the weight and it come back to the normal shape, he never passing elastic limit, yet he started to disobey Hooke's law. Because the rubber band can burst, when it reaches its elastic limit also. But him start to disobey Hooke's law way before him reach film elastic limit, which would start to, disobedience would start to be about here, where this last force is really and truly being added back, getting similar to that extension right there. So this force and that force start behave similar as it regards to distance being extended to. Okay, so that's the difference between the extension graph of why rubber bands do not, or elastic bands do not obey Hooke's law. Their extension graph does not have a straight line, while metal springs and metal wires will give an obedient results and prove the principle of Hooke's law. You might be asking, what does this have to do with me? Let me tell you something. There is no car today on planet Earth that is not built to obey Hooke's law. Have you ever seen those big springs in the vehicles when they put above the vehicle tire, right? Those are called shock absorbers, right? Shock absorbers have to obey Hooke's law. When the car is even placed on the shock absorbers, they absorb the weight being placed on them. When the car starting to move, the starts to actually take off the amount of force that would be exerted upon the wheel from rough roads and rock stone and pothole and all of that thing. Them absorb force. That's why springs are so impressive. A very impressive design, right? They are force absorbers, and they are also because of their ability to compress. So the Hooke's law, it don't only deal with stretching, Hooke's law also deal with compression. Because we could have taken this spring and safe him obey Hooke's law by not merely stretching him, but by compressing him, pushing him closer and closer together. Just because it's harder to measure that kind of force, right? It is easier to measure the force or the weight of an object pulling down on the spring. But to push up the spring, that's a little bit more challenging for any device that we have in the physics lab. But the string could have been a compression force, or it could have been a stretching force. Okay, so that force would be a compression or a stretching force. You can make a note of that. Alright guys, so now we can look at something called the spring constant. The spring constant is exactly what is utilized in engineering to create wires and to create springs. For example, kind of spring where you use make a shock absorber for putting on a car. Even kind of spring where them make silly posturepedic bed. Yes, them rich bed there. Right? All of them spring they have to know. The manufacturers have to know the spring constant. When you know the spring constant, you actually know how much force the spring can take before it reaches its elastic limit and it really becomes useless. Okay, so imagine if you never know how much force a shock absorber spring can take. Yet you go put in a vehicle. And in a reality, although say you never know about the spring that the shock absorber had, right, that was used to make a shock absorber, could only hold 500 Newton of force before he reach him elastic limit. If he reach 500, if he get 501 Newton elastic limit done, and he stretch out and become useless. You go put now a car that weighs 10,000 Newtons, probably weighs more, and that spring and that shock absorber. What do you think is going to happen to the persons who drive it? Their life is going to be threatened, right? Their life is going to be in danger, because when they're going at high speeds, that spring is going to definitely shatter and stretch out. The total deformation under the force become useless. Okay, so you must know spring constant. Spring constant is very easy to calculate, and it is very important in industry. It is defined, and it is based on the principle of Hooke's law. If there was no Hooke's law, we could have no spring constants, right? So we use Hooke's law to determine spring constant. Alright, just to put that out as a statement. The spring constant is defined as the force in newtons needed to stretch or compress a spring divided by the distance that the spring gets shorter or longer, which is the, in bracket, you could call that the extension, okay? Extension distance. So as me say, it could be a compression force, it could be, and if it's a compression force, you would have pushed the spring closer and closer together. You guys can try that with a spring that you have around the home, if you have not done that in the past. Or it could be a stretching force, which would cause it to extend. But in either way, it's merely the distance that the spring gets shorter or longer, given the force that is added to it. Okay, where they add it, we compress it, where they add it, we stretch it. Okay, same additional force. So that is the spring constant. You might ask though, how do I calculate it? Well, that is what I am going to show you now. Spring constant is very easy to calculate. It's really and truly a 3-variable equation. Means that it only have 3 parts. Okay, so there's nothing to worry about. So the spring constant, right, has a unit, and that unit is in Newton over meter, right? That is unit, which can be also written as Newton meter to the -1. That's why me show you this first, so you know mix up here with this. Newton meter, Newton times meter, which is moments. No, Newton divided by distance in meter, as the definition already said. Which if you can convert this, invert it, and get it to be m to the -1 power, right? As I taught you in the past, that when things are divided like that, you can change the per Newton per meter, that's what it is saying, and turn the one that's down here, bringing them up by switching them. You're actually doing this. M, right, because multiply by 1 over m, right? You would get Newton meter to the -1. Okay, so Newton over meter, Newton per meter, is the unit of the spring extension, which is Newton divided by meter. Force divided by meter, otherwise called Newton times m to the negative 1. Okay, it is not the same thing as Newton times meter, because this is coming from that, as me show you with the times 1 over m. Okay, Newton meter, not a lot to absorb, right? Therefore, we can say then that the spring, if we know the unit, we can say that the spring constant is equal to, and we can give it a little symbol, we can call it K. Spring constant K is not its unit. We're just using this as a symbol for spring constant. It's not its unit, that's its unit. Okay, spring constant K is equal to the force, right, F, and that is another symbol I'm using, the force F over extension X. Alright, force F over extension X. Alright, and you could put in your units now, you could say force in Newton and extension in meter. Mind you, the extension distance is not in centimeter this time. When you calculate the spring constant, you must convert the distances from centimeters or millimeters, as obviously some of the spring them we are going to use in the lab, them are going to give you readings in a centimeter. Alright, because when first we don't want to stretch them out and mash them up, we have no long spring. Okay, so they may give you centimeter, you convert it to meter. If you get your extension readings in the lab in centimeter, you convert it to meter when you calculate the spring constant of the spring. So guys, the lab that I showed you from the very beginning, you can use that lab and find the spring constant for any spring. You can find it for any spring, because spring constant is equal to the force in newtons divided by the extension in m. For you know the weight of the object where you put on the spring, and the distance of the spring I will extend to by measuring the distance it extends to, you're good to go. Okay, alright. And if you know the mass of the object, you could have find the weight of the object, because mass equal weight equal mass times gravity, and that is always 10 Newton. May not be directly 10 Newton where you live, alright, but you can use the 10 Newton rough calculation. Okay, so let us put this, we can make it easier. I give you the triangle. Alright, so spring constant K is equal to force over extension. That is the same thing in our triangle as saying force at the top, force in Newton, right? And you put extension in meter here, extension in meter there, that's extension, right? And the spring constant here, spring constant in Newton per meter to the Newton meter to the negative 1, Newton meter to the negative 1. So therefore, any triangle you're seeing that force would be at the top, extension would be there to the top, to the bottom left hand corner, spring constant would be to the bottom right hand corner. If I cover, say for instance, let's see if that agrees with this. If I cover spring constant, what do I have left? How do I find spring constant? I cover it, and it sees that we see that it is found by dividing the force, dividing the extension into the force, just like that. And just like my original Newton per meter unit, the units actually tell you how to calculate the values that you want. The units actually tell you how to calculate. The units are actually the equations for calculating something in physics. As long as it is a derived unit or a derived quantity, right, you can take that unit and use it as the equation. It's actually telling you the equation. Just give you a little side note for those who did not hear it long time when we said. Okay, so do you want us to do a question? Do you need a question? Better you get it from now, because you'll be getting a lot. Okay, you'll be getting a lot. For example, let's do an example then. Let us do an example. Oh yes, mind you. And you can use this triangle here, or you can use the equation there to find not only if they want the spring constant and you have the force and the extension, you can find it. Okay? If you have the mass only, remember I said this force is going to be the weight here. If then you get the mass of the object only, you can convert the mass to weight by multiplying it by 10 Newton per kilogram, which is gravity, right? And find weight. That's easy. And then you can use the force and the extension to find the spring constant. If then you get the spring constant and the force, and then once you find extension, you can find it. By covering extension, you see that extension is equal to force divided by spring constant. If you want to find the force, and then your extension and spring constant, it is easy. Force is equal, or the weight is equal to the extension times the spring constant. Very easy, not true? Yes, man, nothing for scholars as yourself. So let us do one. Right? Let us do one. A car has a mass, right, of 1.2 ton. The suspension springs of the car together have a spring constant, and you can write it down as I say to you. The extension, the spring of the car together have a spring constant of 2 times 10 to the 5th Newton meter to the negative 1. How far does the weight of the car compress the spring? How far does what? How far does the weight of the car compress the spring? What are they asking you for? Obviously, they might ask you for the extension. This is a compression force, because you know, say when the spring car go down on the shock absorber, or the spring them are going to compress close together. No, so? Yes, they are. So they might ask you for how far it compress to. They ask you for the extension distance. In the question, the spring is being compressed rather than stretched. Nevertheless, it is the same calculation, right? And as me did give some symbols, right? I've given you some symbol of f and x and blah blah blah, right? So if you don't want to write out a long equation, which I would love to tell you to do, I'll give you the shorthand one though. Force is equal to spring constant k times the distance x. Okay, F equal k times x. You can use the normal calculation. I would want you to practice that. This one is just for me, right? And if F is equal to k over x, meaning that the force is equal to the extension times the spring constant, right? Therefore, the extension is equal to the force divided by the spring constant, and that is obviously true according to a triangle. So, the extension x, right, is equal to F over k, force over spring constant, okay? You know? And please rewind the question so you can hear what the question actually said. So, the weight of the car 1.2 ton. Can we use that like that? 1.2 ton. No, we can't use ton. We have to get it into the base quantity, which is kg. So ton to 1.2 ton to kilogram, right, is what we need to convert. We need to ask ourselves, how many kilogram make 1 ton? Right? Or how many ton? How many kilogram make 1 ton? The conversion factor is 1,000. If you never know, now you know. 1,000 kilogram is equal to 1 ton. 1,000 kilograms make 1 ton. Therefore, if I have 1.2 ton, how much kilogram do I have? That is easy. 1.2, 1,000 times 1.2 is equal to 1,200 kg. 1,200 what? Kg. Alright? Now we have mass. Can we go and calculate? No, because according to this, we still need my force. I need my force, right? Are you seeing it? I need my force. Because the equation say, right, the extension is equal to the force, which is the weight, divided by the spring constant, okay? Which is, we summarize that to be extension, which we place as x in the first part of the equation, is equal to the force over spring constant k, and that's k right there, okay? Right, so we can't just go ahead and use mass. Kilogram measures mass. I need my weight, and my weight is the force, right? The force here is going to be the weight of the vehicle. So what do I do? Weight, as we do from another triangle, weight, which is a force, same way, right, is equal to mass times gravity. You would have known that from the moments video. Mass times gravity, right? So now you know say gravity is always 10 Newton per kg, right? So now 1200, right, times 10 Newton per kg, and this would have been 1200 kilogram, right? Kg cancels kg, leaving me with 1200 times 10, right? How much is that? And you can rewind if you want that note. How much is that? 1200 times 10, right? 1200 times 10 is 1.2 times 10 to the 4th Newton. 1.2 times 10 to the 4th Newton. Yes, that's a big value. 1200 times 10. Okay, that is a lot. So you summarize that in standard form as 1.2 times 10 to the 4. Please know, you have to practice using a standard form. Okay, guys, 1.2 times 10 to the 4 Newton. Right? Now, can I go ahead now, since I have my weight, which is my force, and calculate spring constant? Can I do that now? And calculate the extension force rather. Can I do that? Yes, I can. So, according to the equation, extension force, and you would have written the equation already, extension is equal to the force, so that's 1.2 times 10 to the 4th Newton divided by the spring constant, which is 2 times 10 to the 5th Newton meter to the negative 1, right? So Newton would have cancelled Newton, right, leaving me with meter. Okay, are you seeing it good? So that's 1.2 times 10 to the negative times 10 to the 4th, not negative 4, 10 to the 4th, divided by 2 times 10 to the 5th Newton per meter. Alright, Newton cancel Newton, and now 2 times 10 to the 5 divided into 1.2 times 10 to the 4. How much is that? Right? That gives me 0.06 meter, right? Or in standard form, 6 times 10 to the negative 2 meter. 6 times 10 to the negative 2 meter, right? And if we want it in centimeter, 0.06 meter to centimeter, or 6 times 10 to the negative 2, and obviously you see how me get me 6 times 10 to the negative 2. 1, 2, right? So 6 or 6.0 times 10 to the negative 2. I move 2 places away to the right from the decimal point. That's how I got to the negative 2. Alright, so in centimeter, that would actually be 6 centimeter. You can go ahead and verify, right? So you'll be getting questions similar to these. You have learned about Hooke's law. You have learned about spring constant. You should be able to define spring constant. You should be able to state Hooke's law from memory. You should be able to know the parts of a Hooke's law graph. You should be able to define elastic limit. Where in a Hooke's law graph is Hooke's law obeyed, and where on the graph it is not obeyed. You should be able to do all of these things and to answer questions like these, which I already have prepared and is going to give to you. Okay, enjoy.